Good morning, everyone. So let's wait for one more minute. Maybe others will join in soon. Meanwhile, if you want to discuss anything, we can do that. If anyone has any questions, please speak up. Anyone with any questions before we start? Okay, there are no questions. Let's begin. All right. So today we are going to discuss this concept of overfitting first. Okay. So I'll give you a small analogy what overfitting is. See, the idea is that you are trying to learn machine learning models from a given data set. So let's say if I give you a data set, probably which has, say, 3 examples. Okay. And there is just one input feature. This is just a demonstration. Okay. So I am giving you this one input feature data set. So you will have a data set like this. Okay. You can say you have one input feature and the output is Y. Okay. So what you typically do is, so given any data set, you split it into train and test, right? You make it into 2 parts. Now, once the data set is split, from the training set, we are going to learn the model. So imagine this is the training set. So we have some data set which has, say, 3 examples. I'm just giving you a synthetic idea here. Okay. So let's say these are the 3 examples that you have. Maybe say this is A1, B1, let me call it A1, Y1, A2, Y2, A3, Y3. Okay. So just by looking at it, can you tell me what kind of function will fit the best? A linear, quadratic, cubic? Linear, right? Just by looking at it. So you apply linear regression to it without creating any new features because you want linear. And what is the prediction equation for a linear function? If you have one input feature?
Theta 1 x1 plus theta naught.
Theta 1 x1 plus theta naught. Absolutely spot on. Okay. So if you try to plot this, this will come out to be a line. So if you apply linear regression, so what you are doing is you are minimizing this, right? Yi minus yi hat whole square, where yi hat is this. Okay, let's say I here. Okay, where yi hat is this. Okay, so you apply it onto these 3 examples. Your goal is to minimize this equation, this optimization equation, and you are doing it with respect to the 2 thetas that you want to determine, which is theta naught and theta 1. This is the objective, right? When you are trying to learn the thetas, this is the objective that you are trying to minimize, the sum of squared errors. You can put any constant also outside, say 1 by 2, 1 by n, 1 by 2n. All of them will give you the same thetas. Now, if you try to minimize this, I'll just ask you this. Okay, I'm going to draw 2 lines. You tell me which is better. So maybe say this is one line. Let's call this as line L1. Okay. Let's say this is another line. Let me make it a different color. So this is line L2. So which line do you think you will achieve, L1 or L2, when you minimize this equation on the training set?
L1.
L1, right? Because you are trying to find that line which minimizes the sum of the square distances. And because these 3 points are collinear, As you can see, these 3 points are collinear, right? 1, 2, and 3. These 3 points are collinear. You will find that line L1, okay, if you try to minimize this. Now the question comes, is it guaranteed that line L1, can you guarantee that, okay? Is it guaranteed that line L1 is the best line for test set also?
No.
No, right? I mean, it's not guaranteed, okay? So the answer is no to this. So is it possible that L2 can be the best line?
Yes.
Maybe, right? I need to just test on it. Using the equation of line L2, I can test, okay? So, but can I say that L2 has more error than line L1? Yes or no?
Yes.
Okay, now the solutions that you have studied, they will directly give you line L1. Do you think you can get line L2 from it? Any of the solutions that you have studied, do you think only gradient descent can give you line L2? So you are, let's say, updating the thetas. You may reach in a situation L2 and maybe say in the next iteration from L2 you reach L1 because you will update the thetas, right? So from L2 you may reach L1. That is, so gradient descent can give you line L2. So let me tell you, since you have studied gradient descent, right? So in gradient descent, there is one more convergence criteria. Okay. And the convergence criteria says is this. So when you're starting your model training, right, you have a training set. So what we do is we split it into 2 parts, training and validation. Okay. Training and validation. So what we do is using the training set, we update the thetas. Okay. We update the thetas. And validation set is like very similar to a test set. It's an unknown data set. You don't use it to update the thetas. So using the updated thetas at every step, can I evaluate some evaluation metric? Can I find some evaluation metric? So evaluate on the validation set. Okay. So I am going to stop at that point. See, typically how gradient descent starts. You start with some value of your thetas, right? Assume that you started like this. This is the initial line. Then you will update this line. You will update the thetas of this line, right? Using the data set. You will go in the opposite direction of the gradient and you will keep on updating it. So maybe in the next line will become like this. 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 And maybe then you reach this line L2. Okay. And after L2, say you reach L1. Okay. So what you're doing is at every step, once you're updating the thetas, at every step, you are checking the line that I get in the next step. Is it better for the validation set or not? If it is better for the validation set, can I say that I can stop? Because if you remember, originally the data that you have, right, you split it into train and test. Because the data is split from the same thing. It is, it can be assumed that something which is doing better on the validation set can also do better on the test set, right? Yes or no?
Yes.
So that's how, so this is like using a validation set, you can decide when to stop. So when the performance, so which metric do you want me to use? You can use any regression evaluation metric. Tell me which regression evaluation metric let's use.
Mean squared error.
So let's say when MSE starts to decrease. See, if it increases, I'm going to update the thetas. When MSE starts to decrease, don't you think I can stop? Yes or no? Okay. So that is the idea. So gradient descent is the only algorithm that you have studied. Okay. That can give you these different lines on which you can evaluate. But any other solution that you have studied, right? Like the closed form solution, or say when we took the derivatives, equated it to 0, we will directly get this line L1. Okay. So can we modify those solutions? Okay. Can we modify those solutions to find those thetas which are working better on my test set? That is the goal. So do you agree with me when I say that line L2 has more error? Yes or no? Line L2 has more error with respect to L1.
Yes.
Okay. So the concept of overfitting says that when your model does exceptionally well on the training set, okay, when the model performs exceptionally well on the training set, however, it does badly on the test set. Okay. So performs miserably on the test set. So to avoid this, what can be done is, okay, see, the solution to all of your problems is data. One of the solutions is you get more data in the training set, your results would improve. Because the more data that you have, the more is the chance that you will perform better on the test set. Okay. The more data that you have, better is the chance that you will do on the test set. But however, this solution is not practical. Where do you get this data first? If you had more data, don't you think you would have used it in the training set already? I mean, that's a counterpoint, right? So solutions to all your problem is getting more data, but getting more data is expensive, time consuming. Okay. Who is going to label it for you? Not every data that you see has an output indicated next to it. Okay. Let's say we are talking about images. And I want to identify how many objects are in a given image. Do you think for every image you would know how many objects are there? Will internet tell you, okay, for this image, these many objects are there? Don't you, I mean, can you think that, okay, for every image, I have to assign someone to figure out, okay, how many objects are there? And that person will tell me how many objects are there. Yes or no? So there has to be someone who will label the data for you, who will give the outputs to you, right? For that, to that person, you will have to pay. And this process is time consuming because for every image, that person needs to sit. This is a very simple example. Think about what will happen if you go to, I would say, very niche domains. For example, medical domains. Do you think a regular person can do it? No. Maybe you need to reach out to expert doctors. You will have to pay them. So getting more data is the solution, but that is not practical. It's not feasible at all. The other thing that we can do is, this is the concept. So one solution, as I'm saying, is get more data. Okay. But that is not feasible. Okay. This is not practical. Okay. In most cases, it's not feasible. Yeah. I mean, if you are working for a rich industry, yes, you can, but that will be time consuming. You'll have to wait. Okay. The other solution is, let me call it the second solution is, you do something called as regularization. You do something called as regularization. And what it says is, you deliberately penalize your model. You deliberately penalize your model so that it does not achieve, so that it does not overfit. Okay. So that it does not overfit. Okay. So the more you penalize, the further you will be away from the best solution, from this line L1, from this line L1. Okay. So what is meant by this penalty? The penalty is a very simple concept. Okay. So since we are trying to minimize this function, yi minus yi hat whole square, okay, you can have 1 by 2, 1 by n, anything outside. Okay. Currently, we are trying to minimize this. I'm taking just one dimensional example. Okay. Where yi hat is theta naught plus theta 1 x1 I. Okay. Yeah. All right. So what you do is, in addition to minimizing this, okay, in addition to minimizing this, you add one more term to this. Okay. You add one more term to this, and you call this term as the penalty function. You call this term as a penalty function. This penalty function is a positive term. It's a positive term. Okay, it's a positive term. And you are going to multiply this penalty function with the factor lambda. Lambda is also a positive term. Okay, lambda is also a positive term. Okay. Now, think. Okay, I just want you to think for now. If lambda is 0, can I say that I will achieve line L1? Yes or no? If lambda is 0, can I say that You will achieve line L1.
Yes.
Okay, because there is no penalty in that case. If I make lambda to be high, you will probably reach line L2 or some other line which is closer to probably L2. Okay, far away from L1, but you can say that okay, it will have some more loss. So it will not be fitting to these 3 points that I'm showing you. Okay. The more you add the penalty, maybe you will reach L2, and maybe you can reach far away as well. Okay. It depends on how much penalty you add, right? So let's see what are these penalty functions. Okay. Please note that they will be functions. You cannot simply add a number here. If you add a number, okay, let's think about this. Let's say I'm minimizing a function with respect to a variable. If I add a constant to this, let's say 10, do you think X changes?
No.
No, right? So it has to be a function. And what this, I mean, in terms of what this function should be?
X.
X. So in my case, the penalty function should be in terms of what?
The thetas.
Thetas. Okay. So we are going to add a function in terms of the thetas. At least one person understand. Okay. You guys also correspond as well, others also. Okay. Thanks, Shilpa. Okay. So you'll be adding these penalty functions which are positive. So if you think about it, one of the penalty functions that I can add in terms of thetas, which is always positive. Can you think like simple function in terms of my thetas, okay, which is always positive? Use only thetas, which is always positive. Think.
Square function.
Square function. Maybe I can sum all the squares of the thetas. Yes or no? Let's say there are d thetas. Okay. Let's say there are d thetas. Let's say I'm going up to theta d. See, you can think of polynomial features also. No one stops you. You have x1, x1 squared, x1 cubed, maybe x2, x2 squared, x1, x2, whatever features that come to your mind. Make those feature sets. You are trying to learn one theta for each of them. Now I'm saying that you add a penalty function, which is the sum of the squares of the thetas. Okay, this is sum of squares of all the thetas. So this is equivalent to saying theta 1 square plus theta 2 square and so on till theta d squared. Please note that you do not add for theta naught. You do not add for theta naught. The reason is theta naught is not for any feature. Okay. Theta naught is the intercept term, right? It is not there for any feature. Okay. That's why we add it only for theta 1, theta 2, and so on. Okay. All right. I mean, even if you add for theta naught, it's not going to create any difference, but there will be a problem which I will talk about. If you want to know about that, we can talk about it. If not, you can just skip it. Okay. There is a slight problem if you add theta naught to this. Okay. But it will still work though. Okay. It will still work though. Okay. Now the other thing is this. Can you think of another function? Can you think of another function?
It has to be differential only.
No. Don't think about making it absolute. Okay. There are other solutions to do it, right? I told you linear programming. There are other solutions to solve it. I mean, you don't need to know it, but you can add this penalty function, right? Sum of the thetas. Okay. Sum of the absolute of the thetas. Okay, so these are the acceptable functions. Okay, these are the acceptable functions. Let me tell you about these functions. They have special names. This is also called as L2 penalty. 2 here signifies the power. So this is also called as L1 penalty. Okay, all right. So if you are doing this, minimizing, say I, so I here is on samples. Okay, the I here is indexed on samples. Yeah, sorry, this is indexed on n samples. If you have your data set with n examples, I is indexed on samples. Yi minus yi hat whole square, where yi hat is theta naught plus theta 1 x1 I, theta 2 x2 I, and so on till theta d xt. Okay, let's say you are adding this lambda times this j equals to 1 to d theta j square. Okay, this is the squares of the thetas. Okay, squares of the thetas. So squares of the thetas. This is your L2 penalty. Okay, some terminologies you should know. If you are trying to minimize this whole thing with respect to all the thetas, see, as you know, squared functions are differentiable. And this squared function is also convex. Sum of two convex functions, I'm telling you, there is a property which ensures that sum of two convex functions is also convex. Okay. So this is a convex solution. So you will get just one absolute, one solution for all the thetas. Okay. If you want to solve this together, so minimizing the sum of squared errors, you can put any constant also outside. There is no harm in that. Minimizing the sum of squared errors, or you can say ordinary least squares with this L2 penalty, is also called as ridge regression. There is a name for it. This is also called as ridge regression. Okay. There is a special terminology which people use for this lambda. This is also called as the regularizer. This regulates the penalty, how much the penalty is. Regularizer regulates the penalty, increasing. So lambda is always greater than 0. Please note this. So if it is 0, there is no penalty. If it is higher, it will be more. Okay. All right. One more thing I want to share is this. There is a closed form solution for this. Okay. So the closed form solution for this is, you don't need to remember this. Okay. But if you can remember, that will be great. Okay. This is just letting you know. So if you solve this whole J with respect to theta naught, theta 1, so I'm telling you about the matrix based solution. X transpose X plus lambda times I whole inverse X transpose Y. So these are all your thetas. So in X, don't forget to add the column X naught. When you're solving for this, right, don't forget to append the column X naught, which is always 1. So you can get all the thetas using this solution. Okay. So this is the solution to this.
I over here is the identity.
Identity matrix. I over here is the identity matrix. Identity matrix of size d plus 1 times d plus 1. Okay. This is the identity matrix of this size. Okay. I'll just mention it. It is actually identity matrix of size this. It's written like this. Okay. When you write it, right? That's the people, that's a notation which people use. Okay. So only along the diagonals, you will see a 1. Okay. Only along the diagonals, you will see a 1. Okay. I just want to mention one more thing here. So this J that you see, right? This J that you see, it is indexed on features. Okay. So this is called as your ridge. Okay. We will use this just like linear regression. Okay. So if somebody asks you, what is the hyperparameter here? What is it that you need to tune here? What would you say?
Lambda.
Lambda. So you will do a grid search on lambda or a randomized search on lambda to find the best solution. Okay. To find the best solution. So lambda is essentially your hyperparameter. Please note that in the implementation, this lambda is also called as alpha. In the implementation, it is also called as alpha. It is called as alpha there. Okay. This is also called as alpha. Okay. In the implementation, you will see that, okay, it is called as alpha. All right. Now let's think about the other scenario where I'm doing L1 penalty. So many people will call this as L2 linear regression or L2 regularized regression. So you can also call this ridge regression to be L2 regression or L2 regularized regression. Okay. So some people also call it as L2 regression. Okay. Keep that in mind because some books will refer to it as L2 regression. Some will say ridge. Some will say L2 regularized regression. Okay. But the most common name is ridge. Okay. It's a special name that is given to it. Okay. Now, the next solution is this, that you are trying to minimize the same sum of squared errors with respect to all your thetas. And now you have a positive penalty with terms of absolute thetas. Okay. Now, this, as you know, is called as L1 penalty. Okay. The whole thing, this whole thing is called as lasso. Least absolute shrinkage selection operator. A special name for it. These least absolute shrinkage selection operator. That's a fancy name for it. Okay. Now, this is not differentiable because this function, even though it is convex, okay, this function absolute is not differentiable. So, I mean, we have not studied any technique how to solve it, but let me tell you, it typically uses linear programming to solve it. Okay. So, there is no closed form solution for this as such, but you can solve it using linear programming to get the updated value of your thetas. If you're interested, read about it. I do not have the time to discuss it. I'll require at least 4 hours. I was given just 2 hours to discuss linear regression. I've already taken 7 hours. I don't want to go beyond. Okay. So if time permits at the end, I'll take it up. Otherwise, no. Okay. If you're interested, I mean, I'm just letting you know, if you're interested, you can read about how to use linear programming to solve this equation. Okay. Now, using this lasso, okay, you can call it as L1 regression. You can also call it as L1 regression. Now, there is one thing which I forgot. This component, right, the combined component, this is also called as the regularization term. The combined component is also called as the regularization term. Okay. So the total term tells you how much penalty is there. Okay. Total term tells you how much total penalty is there. This decides total penalty. This term decides total penalty. Okay. The combined effect of both of them decides the total penalty. Okay. Now, okay, I just want you to think. You are going to add the sum of the squares of the thetas or sum of the absolute of the thetas. If you want to minimize this whole equation together, can you say what is going to happen to your thetas? Will they increase or decrease? What about their magnitudes? You're going to minimize this equation, right? Yes or no? You're going to minimize this equation?
Yes.
That's your ultimate objective, right? So when you want to, and look at these terms, do you see that each of these terms is positive? Yes or no? Each of these terms is positive, right? Sum of all the thetas. So see, individually thetas can be negative. I'm not denying that. But if you look at the penalty functions are always positive. So can you tell me what is the objective of this penalty function? I mean, when we are adding this deliberate penalty, what is the impact of this penalty on the thetas? Will it increase the magnitude or decrease the magnitude? In general, let's talk about that. In general, what will happen to the magnitudes? You want to overall minimize this function. So what will happen to the magnitude?
Thetas will decrease.
Thetas will decrease. The magnitude will decrease. You cannot say that thetas will decrease. Because if they are negative, they will increase.
Yes.
They will move towards 0. Okay. So ultimately, the impact of these penalty functions is, okay, that your thetas are going to become smaller and smaller. The magnitudes of the thetas are going to become smaller and smaller. And do you know what? One of the indications of overfitting is when the thetas become too high. Let's say that if someone asks you, how do you find if a linear regression model with even polynomial features, if it is overfitting or not? One of the indications is if the thetas are too big, the magnitude of the thetas are too big. That is why we do penalty. Okay. So our ultimate objective is to reduce the magnitude of the thetas. So what regularization does, in simple words, okay, it reduces the magnitude of the thetas. You can say it reduces the importance of the features. Okay, not for all of them, only for the important ones, non-important ones. Okay, it reduces the importance of the thetas. Okay. It reduces the coefficients of your thetas. Okay, sorry, importance of your features. My bad. Okay, that's the, in simple words, that is what regularization is doing. Now I'm going to tell you what do you achieve if you do L1 or L2? What is their impact? Okay, how do they differ? When to use L1, when to use L2? Okay, so there are two subtle differences between L1 and L2. Okay, so if you are using L1, okay, if you are using L1, one of the key things to note is this, and this I will show you in experiments also, that if you increase lambda, what you will see is that most of the thetas will go to 0. When I say most of the thetas, I'm talking about their magnitude. So you can say thetas also go to 0. Okay. So the magnitude will become closer and closer to 0. In L1, it becomes exactly equal to 0. So if you increase lambda too much, all the thetas, all the coefficients, theta 1, theta 2 up to theta d, except for theta naught, everything will go to 0. So if everything goes to 0, what can you say about that model? You will just get, what will be the prediction equation if all the thetas except theta naught, if they go to 0? What would you call that model? It is independent of your inputs, independent of your features. See, how do you predict finally? Theta naught plus theta 1 x1 up to say theta dxd, right? I am saying that you increase the penalty too much. Okay, you increase the lambda too much. So what will happen is all the thetas will become 0. All the thetas. So importance of every theta is 0. If importance of every theta is 0, I mean, if the theta is 0, what will happen to the multiplication of theta 1 with the feature value? Theta I with the feature value will be 0, right? The only thing that you will get is theta naught. Can I say that for whichever sample that you will feed, the answer will always be theta naught? Yes or no? Whichever sample that you will feed, whatever is the value of x1, x2, x3 up to xd, don't you think you will still get the answer as theta naught? Yes or no?
Yes.
So it is a constant model. It is a constant model. And is a constant model good or bad? It is independent of your features.
Bad.
Very bad model. And what is the R2 score for a constant model? We discussed this. What is that? 0. These are the types of things that they will ask you in the interview. They will try to judge. See, one person is able to answer, so hopefully others should also be able to relate. If you have not studied if you've not gone through my sessions in the past, you'll not be able to answer most of the questions that I'm asking today. Okay, and these are the questions that they'll ask you in the interview. Okay, so don't increase lambda too much. If you increase lambda too much, all the coefficients will go to 0. Okay, so in L1 there is this problem. Okay, so can I say that if I increase lambda moderately, some of the thetas will go to 0? Yes or no? If I increase lambdas moderately, some of the thetas will go to 0. Not saying all of them, but some of them will, right? So can I say that Lasso does implicit feature selection? You remember we did recursive feature elimination yesterday. What you were doing is you were dropping the features, right? So we were explicitly doing feature selection. Here, if you make some of the thetas to 0, don't you think those features will not even contribute in the prediction? It is like saying as good as like the features have been dropped. Yes or no? You will see that if you increase lambda, okay. I mean, I'm not talking about the extremes. You make it too big. But if you increase lambda moderately, some of the unimportant features will go to 0. Okay, that's the beauty of L1. Okay, and that's why you can say it does implicit feature selection. Okay, because it will reduce the coefficients to zeros. If you want to say for all of them, if the penalty is too much, all of the features are dropped, then you did over feature selection, I guess. Okay, so you have to find a good value for your lambda. Okay, the hyperparameter, the alpha. Okay, Now
So,
let's, yes.
can you please explain this once again? How does my increasing in lambda makes thetas to go to 0?
Okay. Do you want me to give you the intuition for it?
Yeah, I did not get that whole concept. Like, how
Okay, no, I was telling you a fact. This will happen. Now, do you want to know the intuition for it? Why it becomes equal to 0?
Yes.
Okay. See, the intuition is we are trying to minimize these terms together, right? Yes or no?
Yes.
Okay. So I want to reduce these two objectives combined. Okay. Keep that in mind. Okay. So if, let's say, if you think about it, see, the only thing that can happen is the thetas can increase or thetas can decrease. Yes or no? Okay.
Yes.
There are two things only. Okay. I am saying that thetas will decrease. Why they decrease? Let's talk about it. What is your ultimate objective? Your objective is to minimize this. So if you increase the magnitude of the thetas, what happens to the penalty? It becomes more. Yes or no? Because lambda says a constant, right? That you will specify. So if you increase thetas, your penalty becomes more. So are you achieving the objective? No, right? So thetas has to decrease. The magnitude has to decrease. So if a theta was negative, you will push it towards 0, right?
Yes.
So it is increasing in that case.
Yes.
So I'm saying magnitude decreases, right?
Yes.
So that is why I'm saying the magnitude will decrease. And what you will observe is that some of the theta's magnitudes will become equal to 0. If lambda is moderate, if lambda is too much, all the thetas will become equal to 0. All the coefficients rather, not theta naught.
Okay.
Okay, that's what the objective is. Okay, and why we are doing this? Okay, why we are reducing the thetas? The reason for that is like it is an observation when you do these experiments. If the thetas are very, very big, you can definitely claim that the training error would be very, very small, which means that you are overfitting to the training examples.
Yes.
Okay, so you will not generalize well to the test.
Correct.
So we are trying to reduce overfitting, right? So reducing overfitting means reducing the magnitude, and that is achieved via regularization. Okay.
So that means lambda into penalty function I have to decrease. So
overall,
also I have to decrease, and each
Correct.
thing also should be as much low as possible.
As low as possible. Yeah,
So
as low as possible.
Lambda is increasing, so I have to decrease that function so that this whole component is not too high.
Not too high.
So that's why I am decreasing my thetas and decreasing it so much that it is almost close to 0.
You want it to be close to 0, right? But the minimum is not guaranteed to be close to 0.
Yeah, close to 0.
Okay. See, for this example, the minimum will be 0, right? If you think about it, for the example that I drew, because the points are collinear, the line will pass through it.
Yes.
But if I give you a data set like this, maybe I add some more excess here. Can you draw a line which will pass through all the points? No, right? So there will be some error for sure, right? So you are trying to find that least error. Okay. So if there is no penalty, you will find the best line.
Yes.
But if I add some penalty, you are still closer to the best line, but maybe that new line does better on the test set. That's what the objective is.
Okay.
Okay. All right. Okay. Now what happens in L2? See, the concept is more or less the same. If you increase lambda, the magnitudes will decrease. Okay. Magnitudes will decrease, but most of the thetas here, they will not exactly go down to 0. They will become closer to 0. Okay. Will become closer to 0. This is important. Okay. It will not be 0. They will become closer to 0. Okay. Keep that in mind. It does not truly eliminate the importance of all the features. Lasso eliminates it. Okay. The lasso penalty, the L1 penalty eliminates it. Okay. It eliminates the importance of the features at all. L2 does not do that. Okay. The rich penalty does not do that. Okay. Now, do you want a reasoning for it, or you can digest this as a fact? I'll show you in the experiments, or do you want a reasoning for it? Why does this happen that, okay, ridge is not exactly closer to 0, but the other is exactly close to 0, exactly 0? Do you want a reasoning for it? Or shall I just drop it? See, nobody's going to go into that detail. But if you want a reasoning, I can give you an intuition for this. Do you need a reasoning for it? Tell me, please.
Yeah.
Okay. So, all right. Let me give you a small idea. Okay. Okay. Imagine you are, say, doing gradient descent. Okay. You can do gradient descent on this function also, by the way. You can take this function, take the opposite direction of the gradient for L2, I'm saying. You can still minimize this. There is no harm in it. Okay. All right. Now let's 1 second, please. Sorry, guys. Yeah. So let's discuss why this L1, L2, and I mean, why in L1 it goes to 0 and why in L2 it doesn't go to 0. Okay. So this is like a simple mathematical intuition. I am having this as my prediction function. Theta naught plus theta 1 x1 up to theta 2 x2 and so on. Okay. I hope you have realized by now both of them will reduce the thetas. The magnitude of the theta. I shouldn't say thetas will be reduced, but magnitude of thetas will be reduced. Okay. They will become closer to 0. Okay. But why is it that L1 goes to 0? I'm going to talk about that now. Okay. So I'm going to take a small example just to illustrate something. Let's take any two thetas. Let's say theta I and theta j. So theta I is for feature xi, theta j is for feature xj. Okay. So one simple question is this. Let's say theta I is say 100 and theta j is maybe say theta I is minus 100 and theta j is say 5. Can you tell me which is more important? Which feature is more important, xi or xj? In general, let's say if I start with these theta values, which feature will act more important initially?
Theta I.
Feature xi will act more important because the magnitude of theta I is higher. Okay, good. Now let's see this. Okay, let's say I'm doing L1 regression. I'm doing L1 regression, the lasso regression. You know that, okay, thetas will be decreased. So let's try to observe the impact of decreasing the thetas. Okay, let's say I decrease the thetas by 1. When I say decrease, I'm talking about the magnitude decrease. Okay, so you are having this penalty, right? J equals to 1 to d. You are summing up all the thetas. Okay, you are summing up all the thetas. That's what you are doing. You're summing up all the thetas. That's what you're doing. So initially, if I talk about sum of theta I and theta j, what is the penalty? Let's focus on the penalty term only. This is just a simple mathematical intuition. So how much is the theta I and theta j contributing towards the penalty? What is the contribution of theta I and theta j in the penalty term?
105.
105. So 105 is the contribution of xi and xj. Okay. All right. The contribution right now is 105. Okay. In this term, in the penalty term. Okay. Now, you know that, okay, magnitudes are going to decrease. Let's reduce, okay, the magnitude of both of them by 1. Okay. So 5 goes to 4 and this goes to minus 99. Okay. Magnitude has decreased by 1. What is the contribution now?
103.
103. Okay. So if I reduce them, okay, okay, think about this carefully. If I reduce them by the same quantity, if I reduce the magnitude by the same quantity, do you see that both of them contributed 1 and 1 each?
Yes.
Okay. So if a theta was smaller, don't you think it will hit closer to 0? Because if I subtract the same quantity from every theta, that theta will go to 0. Yes or no? That theta will go to 0 quickly, right? Does that make sense or not? Can I say that every feature is kind of having the same impact here? If I reduce the same quantity from every theta, ultimately it goes to 0 and you are not going to add anything to it afterwards. If you add anything to it, what will happen? The penalty will increase. So once a theta goes to 0, do you think you will add anything to it?
No.
No, right? So it will stop there. Okay. So there might be other thetas. So when do you think this theta j will go to 0? Assume that I'm subtracting 1 at each iteration. After how many iterations this 5 will become a 0? After 5 iterations, right? 5 will be 4, 4 will be 3, 3 will be 2, 2 will be 1, 1 will be 0. Okay. And what will be the impact on 100? It will reach to 95.
Yes.
Okay. Now, this one has gone to 0. So if I do one more iteration, 95 will become 94. But do you think 0 will become a 1 or minus 1? No, because that will increase the penalty. Yes or no? Does that make sense?
But how will that stop for theta, like for xj?
No. But do you realize that if some theta goes to 0, it will not change afterwards? Because if you add some more theta, add some more in the theta, even if you go to the negative side of it, the absolute sum will increase, right? The penalty will now increase. It will not decrease then. Ultimately, our goal is to minimize this objective, right? If one of the thetas is 0, imagine that this another theta xk is there, which is 0. Now, can you tell me, do I reduce something for it? Let's say if I make xk as, I'm subtracting 1 from everything, okay? Why did I add 1 to it? Think about this. Because my objective was to decrease 105 to 103. If I subtracted, let's say 1 from this will become minus 101. What is the overall penalty now? 105 again. Yes or no?
Yes.
So it didn't decrease anything, right? Your objective is to minimize this whole objective function, right, with respect to the penalty. So you have to decrease it always. So do you realize that now, once something reaches 0, it will not increase any further. It will not be decreasing, it will not be increasing. It will stay 0. Only other thetas will then move towards 0. Yes or no?
So that means in this summation theta j, right now I'm doing theta I plus theta j till the time theta j, because here theta j will
Correct.
become
0. So if you reach to a situation where theta j reaches 0, okay, then after this it will not change.
So then in my this summation component, I will not have that theta j component and rest.
No, it will be there, but the value is 0. It is not contributing at all.
Okay, so it will not change, but it will be there.
It will be there. Okay, but please note that. Yes, go on.
Doing feature selection.
So if ultimately if theta j is 0, okay, it's not going to change. Okay, let's say if theta j is 0, do you think xj plays a role?
No.
So it is as good as saying you drop the xj from the data set. That is feature selection, right?
Yes.
Okay. That is why I'm saying it is implicitly doing feature selection.
Okay. So it doesn't go beyond 0.
It doesn't go beyond 0, right? Because if it increases beyond 0, you are adding to the penalty term.
Okay.
Okay. But that's not the only thing, okay? Because there is this other term also. This first term that you're minimizing. Okay. You have to think of the difference between the actual and the predicted values as well. So they are kind of in a trade-off. Okay. They are kind of in a trade-off. You have to reduce the thetas so as to ensure that this term is also together minimized. Okay. This term is also together minimized. Yes or no? The impact of this also will matter, right? You are doing the sum of both the terms. If you assume that okay, theta j goes to 0, maybe this term becomes higher. If theta was really important, what will happen to this? This will become higher in that case, right? Okay. So the ultimate goal is to reduce both the terms together such that thetas are decreased. So you have to find up to a value of those thetas, okay, where they have the least magnitude as possible. So some of the thetas will actually have the least magnitude as 0. They will not contribute at all. Okay, they will not contribute at all. All right. Does that make sense or not? Tell me, please. Okay, so both the terms have importance here. Okay, think about this. If I make lambda as 10,000, which term has more importance? The left one or the right one? If I make lambda as 10,000.
Right one.
So if right one has more importance, how can you minimize it? That it is going to focus more on minimizing the thetas. It will not focus on the term 1. So how can you minimize the right hand side term when all the thetas go to 0? So in that case, this term is going to become big. But if thetas were something, you're going to multiply it with 10,000. Okay. So ultimately, it focuses on the right hand side. So all thetas go to 0 except theta naught. That's why you achieve a constant model.
Okay.
Okay. That's why you achieve a constant model. Okay. So the impact is you're trying to reduce this impact of overfitting by reducing the magnitudes, ensuring that the two terms together combined give you a small magnitude. Now, let's talk about why this doesn't happen in L2. Why it doesn't go to 0 exactly. So can I say that in L1, all the features are almost carrying the same importance? I mean, the magnitude that I'm decreasing, I can reduce from almost the same amount. And once they reach zero, it's not going to change. It is just a slight idea. If it hits you, then it's okay. I'm going to show you now that why it will not happen in L2. It will not exactly become zero. Okay. Let's see this. Okay, let's see this. I'm still taking the same example. I have xi and xj. Xi is minus, theta I is minus 100. And theta j is the importance for this. Theta j is 5. Okay. So what is the original penalty? What is the contribution in the original penalty?
105.
No.
No, squaring both.
Yeah.
So it's
25. 10,025. Make sense? Yes or no? It makes sense, right?
Yes.
Okay. So if there is a zero mistake, okay, you can correct it later on. Okay. All right. So now the idea is this. Let's subtract the same quantity from everything. Do you think it contributes equally? Okay, think about this. If I subtract one, if I subtract one from the magnitude, let's say I make it minus 99 and I make it, say 4. Reducing what quantity gave me more reduction?
100 to 99.
100 to 99, right? How much did I actually reduce?
Whatever is the difference in the square of these two.
So what is the difference? So 100 square minus 99 square?
A square plus B square. 100 minus 99 and 1.
Does that make sense? And what is the difference in the other one? 9. Does that make sense or not? So in one case it is 199, the other case it is 9. Okay, keep that in mind. All right. So can I say that this L2 is going to focus more on higher weights first? Yes or no?
Yes.
It is going to quickly reduce those higher weights to lower values. Okay. So let's say you are reducing hundreds very, very quickly and you reach to a situation where they become equal to 5. Okay. Let's say synthetically, you reach to a situation where they become equal to 5. Now, there is a contention now that which 5 I have to reduce. Okay. I can reduce both the 5 at the same quantity and I'll reach a more minima, right? Yes or no? So do you realize that initially L2 focuses more on higher thetas? Yes or no? One with more magnitudes. Does that make sense or not?
Yes.
It will focus more on the those importances which have a very high magnitude. So can I say that L2 reduces overfitting more quickly?
Yes.
Okay, it reduces it more quickly. Okay, keep that in mind. Okay. Now, okay, let's say that you are in a situation where you reach to a point that some theta L becomes 0.9. Okay, and some theta J becomes 1.5. Which one will be more focused on?
1.5.
1.5, right? Makes sense because it is bigger, right? The square of it would be bigger. Okay. Let's talk about if some theta I is between 0 to 1. What if some theta I is between 0 to 1? Can you tell me if I square that theta, is it higher or lower?
Lower.
It from 0.9 it becomes 0.81, right? Yes or no?
Lower.
So if you keep on squaring it up, do you ever reach a 0? Think about it. You're trying to reduce it, right? You keep on squaring this penalty term. Will you ever reach a 0?
No.
Take any fraction. Do you ever reach a 0? Even if you do it infinite times, you do not exactly reach a 0. It becomes 10 to the power minus 21, 31, 41, 51, and so on. Doesn't reach a 0. Okay. And so can I say this, what this L2 will do? As soon as you hit the updated value of theta between 0 to 1, it does not focus on those values at all. It focuses only on those values which are higher than 1 and tries to reduce them, tries to bring them down between 0 to 1. And if you keep on squaring it up, it will still not go to 0. Never ever you will see that the coefficients in L2 will go to 0. You will see they will become very, very small, 0.00000, and never they will reach a 0. Okay. Even if you increase lambda to say 10,000, the alpha value to 10,000, you will still see that, okay, they will become very, very small. They will never reach a zero. Okay. Do you get the intuition now why that doesn't happen? Because as soon as you hit this number of theta between 0 to 1, if you square it up, the penalty actually reduces further. So it doesn't focus on reducing those thetas anymore. Does that make sense? Yes or no? Because as soon as these thetas hit a value between 0 to 1, it starts focusing on this other term, the first term. Because this is ultimately going, this is going to be theta square in L2, right? This is ultimately going to be even smaller as soon as the thetas hit closer to 0. So this term is already contributing less. So that's where it tries to focus on this term, term 1. Okay. So do you realize that now you never reach a 0? To some extent, at least, does it hit you? Yes or no? Or is it still fuzzy? See, this was just to give you the mathematical intuition. I'll show you experimentally this happens. So since you asked this question, okay, why does this happen? Because as you update the values of your thetas between 0 to 1, if you square it up, the penalty is already reduced. So the focus becomes more on minimizing term 1. Okay. So the focus is not there to minimize them anymore. Okay. So then it becomes the question of finding that sweet thetas between 0 to 1, where you minimize this term 1 first. Okay. So the question becomes more focused on the term 1 as soon as the thetas become minimized between 0 to 1. Okay. But in the case of L1, if you reduce them the same quantity, even if they become a fraction, they will still go to 0. Okay. Because every term plays an equally important role. Okay. All right. Okay, so this is the idea of L1 and L2. We will see that experimentally if you increase lambda or alpha, you can say, you will see that in L1 they will reach exactly equal to 0, but in L2 that will not happen. They will become very, very small, but not 0. Magnitude will not be 0. Okay, they can be negative also though. Okay. By the way, when you are solving for lasso, right, this L1, solving for this lasso actually provides you another argument where you can, so the way you solve lasso, people have, researchers have given a special treatment to lasso where they can give you, so in the function that you will see, right, there will be an argument called as positive. If you set it to true, it will always return positive coefficients. It will always return positive coefficients. Okay. When I say positive, they will be greater than 0. If you set this argument to true in the implementation, okay, in the implementation, they will always return positive coefficient. Now, what is the benefit of it? What is the benefit for it? So if all the coefficients are positive, can I say that I can compare them relatively? Yes or no? I don't have to worry about in what direction they are driving the magnitude, because all of them will be driving in the positive direction only. Yes or no? Let's say if everything is normalized between 0 to 1, okay, and the coefficients are also positive, don't you think I can compare them now exactly? Yes or no?
Yes.
Okay, so that is like one advantage that I get with lasso, okay, which I don't have with other functions. Now, when to use lasso or L2? So one of the ideas is when you have a very big data set, okay, then you think about what to use. When you have a big data set in terms of number of features, what would you use?
Lasso.
Lasso. You will try to reduce the number of features. That gives you an added advantage. When you have a smaller data set where you think, okay, most of the features are important, all of the features are typically important in a small data set, right? There you typically use L2. Okay, so every feature carries some relatively good importance, but you still want to find out the optimal theta such that the performance is improved. There you use L2. Okay, so L1 is used for data sets with large features. Okay, used for data sets with large features. Okay. Okay, and L2 is used for smaller data sets. Yeah. Typically, L2 is used for smaller data sets. Okay. So this was the idea behind regularization. So there is one more, which is a hybrid of L1 and L2. See, both of them have their own pros and cons, right? If you think about it. Okay. One exactly lets them to 0. Maybe that feature was somewhat slightly important, but L1 will push it to 0. Okay. L2 will not. Okay. So L2 also has its own importance. It gives somewhat minimalistic weightage to every feature. Okay. So, but if you increase lambda too much, L1 will push most of the features to 0. So you have to be very careful. So that's why there is this hybrid, which is called as elastic net. It's called as elastic net regularization. So what it does is it combines both L1 and L2. The idea is very simple. You are trying to minimize this term 1. What you will have is one component for L1. Let's say lambda 1 times the L1 penalty. The L1 penalty, as you know, is this plus lambda 2 times the L2 penalty. So it kind of regulates. So both lambda 1 and lambda 2 are greater than 0. Okay. And their sum is equal to 1. Okay. So if I say lambda 1 is 0.3, can I say that I'm giving 30% weightage to L1 and 70% weightage to L2?
Yes.
Okay. You can simply replace lambda 2 by 1 minus lambda 1 also. Okay. So how many hyperparameters are there in this equation? Truly. How many hyperparameters are there in this equation truly?
1.
1 only, which is called as lambda 1. So lambda 1 also has a special name. This is called as L1 ratio. The importance of L1. In the implementation, you will see that it is called as L1 ratio. It is a number between 0 to 1. Okay. It is a number between 0 to 1. Okay. Let me say this L1 ratio, lambda 1. It is between 0 to 1. So this tells you, okay, how much to regulate the penalty for L1 and L2 respectively. There is only one hyperparameter. L2, you can ignore it if you want. Okay. Lambda 2, you can ignore it if you want. Yes.
Lambda 1 should always be less than 1, or it can be equal to 1 also, because
If it is equal to 1, what is this called?
L1.
That's it. There is no L2 there.
It will not be an elastic net.
No. Elastic net means you are elasticizing between L1 and L2. So you can go to the furthest end, where it will become lasso. You go to the other end, it becomes L2.
It can be ridge, lasso, or in between.
In between. Yeah, that's why it is called as elastic net. It is elastic between them. Okay. Understood? Shall I go ahead? Yes, people. Shall I go ahead? Tell me, please. If you have any questions, please ask. Okay. I know these are some difficult concepts to digest, but this is the level of clarity that you should have in your interviews, because this is what they will ask. They will not ask you, do you know how to implement lasso? There is just one function lasso that you will use, and there will be an alpha in it. You need to know what they do. Okay. Yeah, I can state it as facts, and I will tell you, okay, this is lasso, use it. But if you do not know what they do, I mean, you will not be able to crack the interviews. Okay. All right. So this was about regularization. So you will see all these things in linear models. Okay. So wherever you're using a linear model, you will see all these things. Okay. All right. So let's see the implementation of these things. And I don't think I'll need more than 10-15 minutes to do this, maybe 20-25 minutes. Let's assume half an hour. So I'll be taking it till 10:35, and then we will directly see classification today. Okay, we will move to classification. So let's implement all of these. Before I do that, any questions, please ask. Yes, people, any questions as such? I don't see any in the meeting chat. Okay, not here either. So I'll move to the implementation now. Okay, if you want to write, You can write to mentor, sorry, the other account, Sanatan, and then, or you can speak up. Okay, let's implement this now. Guys, can you see the screen?
Yes.
Okay, thank you. Okay, let's do everything quickly. Okay, I mean, there is not much change in what we have seen before. Okay. All right, let's take a small data set. Let's go to TOI data sets. Let's take some. Maybe one is enough. Okay, let's take a one with which has a significant number of features. Okay, maybe I'll use this. This has 10 only, but I think this is fine. Yeah. So let's use this. Okay, so X is your data set dot data and Y is your the output. So these are your input features. And this is your output. So you have to predict using these features. So you have to predict using these features how much impact a person has due to diabetes. Okay? I mean, how much diabetes has impacted the health of the individual. If you look at the outputs, higher the output, more the impact has been. So if you look at the first person, so the first person is impacted more in terms of, I mean, in comparison to the second, and so on. Okay. All right. Okay. So I mean, let's look at some descriptive stats quickly. Okay, let's try to describe this. Okay, and see if there is a need for normalization or maximization, or normalization or standardization. Okay, let's do this. One second, this is my data frame. I run describe on it.
Describe would be a function.
So yeah, thank you. And then we have to do the transpose of this, and then you're getting the min and max one. Okay, yeah. So you can see probably the ranges are somewhat different. I mean, they are still very close. So these are the 10 features. We are getting the min and max for them. So, I mean, there is still a need for standardization or normalization. You can do anything. Okay. Which one do you want me to do? Tell me, please.
Standardize.
Okay. So let's standardize them. Okay. So, okay. I'm going to show you. Do you want me to do, say, tenfold validation, or do you want me to just do on a train test split and I try to optimize it for that test set? What is it that you want me to do?
K-fold.
K-fold. Okay. So let's do K-fold. So go to model selection, import K-fold. Okay. All right. And I'll do what we say is, so there is this method called as cross-val score. If you are only interested in getting the tenfold results for a given selection, for a given hyperparameter, this will not do any grid search. This will just give you the K-fold results on any model. Okay. So my model is, let's see this. So my model is, say, linear regression. Or which model do you want me to use? Tell me. Do you want me to compare the results with linear regression also, or shall I directly use Lasso or Reg? What do you prefer? Do you want me to compare the results with linear regression, or shall I directly use lasso?
Compare the result.
Compare the results as well. Okay.
The spelling of standard in this SS equal to standard scalar. Here you are.
Thank you. Okay. All right. Okay, so I'm first getting the results for your linear regression model. So this will directly give you the most optimal solution, but it is not guaranteed to be the best. Okay, let's try to find the best with the help of regularization. Okay, let's define k-fold. How many splits do you want? How many times do you want to run this k-fold? I mean, how many partitions do you want to create?
5.
Let's go with 5. Okay. So let's try to evaluate the linear regression model, okay, on these 5 folds. So provide the model, provide the data, provide the cross-validation technique. Okay, I need to make a pipeline because I have to standardize as well. Yeah. So I'll make a pipeline also. So for your pipeline, you have to first standardize. So provide the steps to this pipeline. Let's make a sequence for our steps. Let's call it as my steps. And provide the steps in a tuple. So I need 2 steps. One is that I want to standardize. Okay, I want to standardize this. Okay, and the other is the next step would be to apply the model. So I'm going to apply this linear regression model. Okay, you can say my model is a linear regression, and you can apply this model.
So in this, rather than in my steps line, where you have mentioned the standard scalar function, rather than
You can
mention
say SS also.
directly as SS also.
Yeah. I mean, but you have to give a name here. Okay.
Yeah. Okay.
The name should be different. I mean, otherwise it will get no. You can keep the same name SS also. That's
That
fine.
will be the step name, and that will be the variable name in which
Variable
I have.
name. Yes. Okay. So whichever name that you're keeping here, that is important.
Yeah. Okay.
Okay. So currently, linear regression does not have any hyperparameters. Okay. So linear regression, I'm directly using to get the say 5-fold results. Okay.
Sklearn spelling in pipeline
Which one?
from sklearn.pipeline.
Yeah. Thank you. Okay. I mean, it'll generate the errors, but thank you for correcting. Okay. Anyways, let's k-fold and scoring metric. What scoring metric do you need?
R2.
R2. Okay, let's go with just R2. So this will, so in my model, okay, you have to pass the pipeline. Okay. So we are going to generate how many values for R2?
5 values.
5 values. Okay, let's see this. So you get these 5 values. Let's take the average to represent these 5 values. Okay. Because I want to know on these 5-fold, what are the results? So these are the 5-fold results. Okay. The average R2 score over 5 folds. Okay. Now this is for linear regression. Okay. This is for the model linear regression. Let's try to do it for say lasso. Yeah. Let's try to do it for lasso. And then compare the results. Okay. So linear regression, please note that it doesn't have any hyperparameters. Okay. So I'm going with say lasso first. Name of the model is lasso. So you can pass this lasso here. I'm going with the default one first. Okay. I'm going with the default one first. I believe that lasso has this alpha to be 0.01. I can show you in the documentation. Probably it's 0.01, the alpha value, or maybe 1. I don't know. It's 1. Okay. All right. So we will implement this. Okay. And then I'll tune on it. Okay. Just wait a sec. So I'm doing it with lasso now. Let's see what are the results. So these are the 5-fold results. This is with the default value. And let's take the average. So this is 0.48197, which is better. Linear is better, right?
Yes, linear.
So I'm going to search for the different values of alphas. Okay. By default, alpha is 1. I'm now going to search for different values of alpha. So for that, I need grid search. So I'll go to grid search. In what range should I search for alphas? In what range do you want to search for alphas?
0.5 to 1.
Okay, 0.5 to 1. Okay, I mean, alphas can go any higher number. Okay, it's not just 1. L1 ratio cannot go higher. Okay, alphas can go 10, 10,000, 20,000, whatever. Okay, so let's say this alpha is my hyperparameter. You have to provide it as a dictionary if you remember. Okay, so let's take some alphas. Okay, I'm starting from say 0. Let's take 0. Okay, maybe says a very small value, not 0. Okay, and maybe I'll go up to 100, and I'm going to take say 10,000 values. Okay. Okay, I'm going to search in this range. Let's call this grid search CV. Okay, let me just copy paste this code so that you guys are able to follow this up all the time. Okay. Okay. All right, let's call grid search CV. Pass your pipeline to it. Pass the parameters. Cross validation technique, which is k-fold. Scoring metric, which is R2. Okay, so this is going to search for 10,000 combinations between this range. Okay, maybe, yeah, this is fine. This is going to search for 10,000 combinations between this range. Okay. All right, so this is done. Let's fit it onto your data. Yes.
Do I have to give this step name also in this params dictionary, or
Thank you, thank you. No, that will, I mean, once I run this, right, it will throw an error. See this, thank you. Which means you are very attentive. Do you see that it throws an error? Yes or no? Okay, it will say that I don't recognize what the parameter is. I mean, invalid parameter alpha for this pipeline. Okay.
step this parameter should
You have to, so to which I should pass this parameter LR.
underscore.
I should say this is last. Okay, let me give it say LAS. So let's say LAS underscore underscore. Thank you. All right. It is just giving you warnings because Lasso is also solved through an iterative solution. So what you can do is just a second. You can increase the iteration numbers. Okay. You can increase the iteration numbers. Maybe make it 10,000, and you can even play around with the tolerance. This is similar to gradient descent. So if the difference in consecutive iterations of your loss function, if it is not changing much, you can stop. Okay, so I believe this is around 0.001 or 0.01. Let me see what is this tolerance. It is around 0.001. You can decrease it so that it doesn't give you this pink warning. Okay, you can decrease this so that it doesn't give you this pink warning. Okay, I believe it's going to take a lot of time. So what I'll do is I'll just stop this. Okay, I'm going to stop this and make subtle changes to it. So this is just for me to show you, right? I'm going to increase the tolerance so it doesn't run for more iterations. I'm going to just keep the tolerance to 0.01. Okay, and maybe this is it. Okay. All right, I will import warnings so you don't see those errors. I don't want you to see those pink warnings. Okay, so that you feel that the model is not running well. Okay. I mean, you can run it in your free time for more iterations. Okay, now it will not show you those pink warnings. Okay, I've increased the tolerance to 0.01. Instead of going for 10,000, let me say I'm searching for 0.01 up to 100. Okay, maybe say 0.05 up to 100. It's 1,000 values here. Okay, let's see what are the best results that you can get with this. I'm just trying to save time. Okay. Otherwise, it will take a lot of time. Lasso is typically slow.
So max iter and this tolerance both are a way to decide till what level should I do this iteration.
Correct. Yes,
Whatever is attained first, it will stop.
but it will stop at that point. Okay, it will stop at that point. So if you want to get the exact same results, okay, if you want to get the exact same results, then mine, okay, maybe you can provide this random state. Okay, if you want to get the same results as mine. So it is very similar to the process of gradient descent, where you assign, say, some initial values. So initial values are assigned through some random function. So if you want to assign the same initial values as mine, provide the same random state. Otherwise, your results and my results would be slightly different. Okay. All right. Let's just run this once more. It will take probably 2 minutes. Okay, this is done. Let's find out what is the best score and let's compare it with the results. Do you see that it is better than what we had over here? That was around 0.4823, if I remember correctly. Yes or no?
Yes.
So we have improved it, but please note that I haven't run it. The tolerance is just 0.001. I mean, even if you run it with the default tolerance, right, it will further improve. If you make it, the default tolerance is 0.001. Okay, 0001, I believe. Yeah, 0001. The results will further improve. Okay, if you run it with this, I don't want to do that because it will take time. Okay. So this is the best score. These are the best parameters, and that is how you achieve your best lasso. Okay. So for this, you are achieving, which means that I can reduce the lasso. See, this is from the corner, right? 0.05. Yes or no? This was my starting value, which means that I can reduce this value, maybe say to 0.001, and it will give me further good results. Maybe I'll show you. Okay, let's say I'm now searching between 0.001 up to say 0. Sorry, maybe let me go like this. Okay, and I'm going between say 0.05. But taking 1,000 values in between, let's see what are the best results now. Hopefully, we will have even better results this time. Okay, hopefully, we'll have even better results this time. Let's wait for 2 more minutes. So this is just to show you how you do grid search. Because, yeah,
Can we do randomized search also over here because it is
yeah, you can do randomized search also. Okay, just to save more time, you could just need to change one thing. Change this function name to randomized search CV here also, and this to param distributions. That's it. Okay. So this is your. Do you see it increased slightly? It is 4.28469. Previously, it was a little lower than this. No, it is still the same. My bad. Okay, maybe then I go to say 0.08 now. Okay, because the next value that I take from 0.05 is what? Just a second. I mean, I need to check from this. Maybe say I go from 0.005 up to say 0.08. Maybe I'll go up to 0.1 and take 1,000 values in between. Just a second. See, it is telling me at 0.05, I'm getting the best results. Hopefully, this time I'll be able to improve upon this value. Okay, let's keep this here. Okay, let's see what is the best score now. You can see it has increased. Okay, so that gives you an idea of how you can increase it. Okay. All right. Okay, so this is your research CV. Now I'm going to show you the impact of like the lasso increasing the lambda. Okay, so let's. But I'll show you directly. Okay, without even doing standardization, normalization. So this is my lasso model. Okay, I'm going to take alpha, which is by the way 1 by default. I'm going to fit to my data x and y, and let's print the coefficients. Okay, can you see that some of the coefficients are 0? I mean, even with alpha equal to 1.
Yes.
Okay, I'm going to make it smaller so that you don't see much impact. Okay. Do you see that now? Like only a few of them are zeros.
Yes.
I'll make it even smaller. Hopefully, these will also become non-zeros. Do you see that? So I'm going in the reverse. Okay. So if you make it 10,000, everyone will be zero.
What is this -0?
Because this was originally negative and it went to zero. Okay. All right. By the way, if you want only positive coefficients, okay, there is a way in case you want positive coefficients. Okay. Let's say currently, can you see that you are only getting negative and positive both? Okay. Yes or no? You have both negative and positive coefficients, right? There is this one argument which is positive, and you can set it to true. And this will always give you positive coefficients now. Do you see that now?
Yes.
So this way you can now compare the argument. I mean, coefficients are positive, and each coefficient is driving in the positive direction. Okay. Sometimes this is helpful when it does not make sense to have negative. You can say negative weights for features. Okay. If it does not make sense to have negative weights for features, you can use this method. Okay. All right. So I'll give you an example. Okay, I'll give you an example where you will use this. Let's say you are trying to determine the cost price of a car. Okay, you're trying to determine the cost price for a car. So you're looking at features like how much metal was used, how much different, how much was the quantity for say aluminium was used, how much the quantity of iron was used, how much the quantity for say carbon was used, and so on. Maybe of a particular alloy was used, and so on. Do you think coefficients can be negative here? Think about it. Let's say you're trying to determine what would be the cost price of, say, what should be the selling price for someone who's about to collect some garbage. Do you think there should be negative coefficients? If the features are the quantities of different items that you're going to sell?
No.
No, right? So in that case, use positive coefficients. Okay. So that would give you actually a better picture of what is happening.
So
Alright.
is there any real-time example where
these are the real-time examples I'm giving you.
No,
I'm not
where negatives are only important?
Negatives examples are, let's say you think about this. Let's say you're trying to determine the amount of rainfall. Okay. If wind speed is high, do you think rainfall will not be impacted?
It will be impacted.
So it will be in the negative direction, right?
Yes.
So, I mean, in most of the cases, you will see that the features that you collect, right? The coefficients have to be negative.
Okay.
When you are doing regression. Finding positive examples is harder. Okay. Okay. Finding positive examples is harder. All right. For most real world applications, right, coefficients have to be negative. But there are only a few scenarios where all of the coefficients you would want it to be positive. And what is the advantage of this? Think about it. If all coefficients are positive, what is the least value possible for a prediction in that case? If all coefficients are positive, what is the least value possible for your prediction? Anyone? It's an interview question. Okay, it was asked maybe in Google or some. I don't remember the exact place, but it has been asked to me as well several times. Think about it. Let's say you're doing this lasso with positive arguments. What is the lowest value of the prediction which is possible? Okay, think about it. Can the cost price ever be negative? You are trying to determine, say, the selling price of an item. Can it be negative?
No.
So if it cannot be negative, what is the least value possible?
0.
Now, if you look at this formula, theta naught plus theta 1 x1 plus theta 2 x2, if all thetas are positive, the features are also positive, right? Because features are the quantities. Let's say they are normalized between 0 to 1. What is the least value possible?
0.
0. Okay. So that's how you can interpret these questions. You have to be elaborate because you have to talk about in what range the features are normalized, because that will also tell you if the prediction can go to negative or not. Okay. All right. So this is your lasso. I'm going to do the same thing for your, say, ridge. Okay. So let's do it for ridge now. Okay, maybe let me first compare it with this. Okay. So this is just to show you that you can use ridge as well here. Okay, but for the ridge, there is no coefficient as positive. Okay. So ridge is also there in this linear model. Okay, and you are going to use this ridge regression. So I'm just going to show you, let's say if I increase alpha, let's see what are the initial weights. Okay, do you see they are negative, positive both and fairly high? I'm going to make it say 10,000. Okay, initially when I made it 10,000, what was the impact by lasso? Everyone went to 0, right? Yes or no?
Yes.
Okay, you can see this now. Okay, now let's see this. Do you see, is anyone going to 0?
No.
Right? There is no positive coefficient here. You can even try harder and harder. Okay, it will still not go to 0. Okay, they'll just become smaller and smaller. Okay, all right, will just become smaller and smaller. Okay, this is just to show you. Okay, let's try to find out the best value for ridge. Okay, this is my ridge now. Please note that there is no parameter like max ITR tolerance for this ridge because I've shown you the formula, right? X transpose X whole inverse, X transpose X plus lambda I whole inverse X transpose Y. Okay. So that is the direct solution, that it is not an iterative process. Okay. So let's fit it onto your data. Let's get the best parameters. Maybe I should have used grid search, sorry, randomized search. Okay, this is done. So this is around 0.4832. Okay, this is certainly better than linear, I believe. Okay, do you see it as better than linear or not? Linear was how much? This was linear. So this was for linear, how much it is right now. It is better than linear for sure. Okay, not better than lasso in this case. I mean, you can try digging it right now. The best value is 0.1. Let's see if I can go higher. Can you see that the highest value is coming here? So I'm trying to now go from say 0.08 up to say 10 and taking 1,000 values in between. Okay. Let's see what is the best value that we get. And I'll keep the best value for alpha here. I believe L2 will do a better job than lasso. Okay. So this was the best score that we got for your lasso. Okay, this is done. It does not reach like this, but the best alpha that I have is around 0.169. Maybe I can do a little bit digging around the corner of 0.169. Okay, so maybe say I'll go up to 0.15. Take say 0, maybe say 2 and taking 1,000 values in between. Let's do some more grid search. You will definitely reach very, very close to this or even surpass this. Let's see. No, it's not going there. 0.4832, 4823. This is still, I mean, I would say 0.0002 places better, but it is around 0.1685. You may go a little closer to this. 1685 would be, so maybe say 16. Maybe say 0.0, say 17. Or maybe say I'll take till 0.02. I'm taking 1,000 values. See if I can improve it even further. Okay. I mean, that's why grid search is a little tedious if you want to beat something. But this is just to show you. No, it's unable to beat, but it's still fairly close. It's 0.0002. Okay. This time it is closer to 0.16. So it is on the left hand side. You can go maybe towards the left a little. I'll stop here. You can do grid search on it. I'm pretty sure that you will beat this number also. I'm pretty sure you'll beat this number. This time it is now 0.145, which means that you can go a little lower than this. Okay. I'll just do it one last time. Okay. Maybe say 0.135, 0.14. Okay. Maybe say 0.145, taking 10,000 values. Oh no, this is fine. Otherwise, this will be too much. But you can definitely achieve this number even higher than this number. It will just take you a little bit more digging. You get closer and closer and you'll be able to beat. So there is this time and results trade-off. Okay, still the same, slightly increasing though. It's 0.145. So you are on the right-hand side. So it says maybe you go from 0.014 to say 0.0147. Okay, something like this. You can definitely get very, very close to this number for sure. Okay, let's see one more, which is ElasticNet. Okay, so with ElasticNet, I'll just show you this. So ElasticNet just controls the L1 ratio. So let me first import ElasticNet. So this is your ElasticNet. Okay, here it is called as L1 ratio, not alpha. Okay, and I'm not interested in the coefficients. Let's say I want to compute the R2 score for this. I'm going with the R2 score. The actual values are in. So I'm using the entire data set. This is just to show you. Anyways, let's see this. Okay. So this is how you can get the ElasticNet model. So this means 10% to L1 and 20%, 90% to L2. If you want to look at the coefficients, these are your coefficients. Okay. If I increase this, more coefficients will tend to 0. Okay. You can see one of them has tended to 0. I'll increase it. So basically, you're giving more importance to L1. Okay. And less to L2. Okay. So if you make it 1, which means only L1 is there, this is becoming equal to lasso only. All right. Okay. You can try with ElasticNet also. Let's do this one time. I'm trying with ElasticNet. So this is L1 ratio here. Okay, and here you have to start from 0 to 1. I'm going with small values, okay? 0.001 up to say 1. I'm taking 1,000 values in between, and this is your ElasticNet. All right, let's run a fit method on this. Let's see the best score and the best balance. Okay, so after this, we'll do gradient descent. So this is the result. You are reaching up to 0.4820. Not very great result. You might have to tune this a little further. Okay. I mean, it's not even able to beat linear regression. Okay. But please note that the best results that you're getting is closer to 0.993, which means that it needs to, it is saying lasso is much better here in this case. So maybe you go to start from 0.095 up to say 0.998 and search in that range. It will make it better. Okay. So you have to play around with this. You have to play around with this.
So can I say like instead of doing lasso and then L2 and then elastic, I can first do with elastic so that the percentage will tell me which one would be better. Because if L1
correct. But see, ElasticNet is actually the most expensive, by the way.
Because it takes both the operations.
It takes more time.
Okay.
I mean, so For smaller data sets, yes, you can do this experiment and see, okay, which is more important. However, I don't recommend using this for bigger data sets. For bigger data sets, directly go with lasso. Forget about using even ridge.
When you say bigger, it is in terms of the
Number
parameter.
of features, parameters, yeah, number of features, yeah. Okay. So this was it. Let's use gradient descent. Okay. So that is also there in linear model. Okay. And the name of the method is SGD regressor, stochastic gradient descent regressor. Okay. So I'm going to show you how to tune it. Okay. Rest everything is the same. Okay. So there's so many things that you can tune in gradient descent. Okay. One is the learning rate. Okay. Let's use gradient descent here. Okay, I'm going to pass a random state here itself so that it doesn't produce different results every time. Okay, I'm going to set the max ITR, maybe say to 10,000, maybe 1,000. Okay, you can change it, you can increase it. Tolerance, maybe say 0.01, whichever is achieved first, it will stop there. Okay, all right. Then do you remember we talked about different strategies?
Yes.
Okay, so first let us try changing the learning rate. Let me say I'm trying for 5 different learning rates from say 0.001 up to say, I'll go up to 0.05, okay, maybe say 0.1. Okay. I'm trying with these 5 different learning rates in between. Then we talked about strategy. Let's see what are the available strategies. Okay, it's a big one. Okay, this one has a lot. You will see this has a lot of the hyperparameters. I mean, see the range. Okay, we have used these two. Okay, you can apply it on different loss functions also. So just like squared error, you have a lot of these different functions. Huber loss, epsilon insensitive, squared epsilon insensitive. I'm going to use some of them. Okay, let's try with loss. Yeah. So squared error is the default one that we have, but you can apply it as long as the function is differentiable. Okay. So if you're able to measure, right? I'm just removing the last one. Okay. I don't want to use, I mean, anything is fine as long as it is differentiable. Then you have these penalties that you can apply. So you are doing now penalties with gradient descent. Okay. So let's try with different penalties. So L1, L2, elastic net. All right. Now, please note this. Elastic net has a special parameter called as L1 ratio. I'm not trying to tune L1 ratio. I'll just fix L1 ratio here itself. Okay. Let's say 0.01. Okay. I'm doing with this. You can tune this L1 ratio as well. Okay. So maybe I'll tune this L1 ratio also. Okay, just a second. I'll tune this L1 ratio as well. Maybe say numpy.linspace. Okay. Maybe say I'll go up to 0 to 1 and maybe taking 10 values in between. Let me tune alpha. Say I'm going from 0.01. I'll run this time randomized search. Okay, I'll go up to say 10, taking 10 values in between. Okay. Anything else?
Step names in param.
Which one? The
Step name.
step name as in?
The parameters that you have given the dictionary.
Yeah, I'll do that at the end. I'll do that at the end. Yeah.
And in this the gradient search that you have mentioned, the
Mhm.
gradient descent, sorry, in that what do you say, the elastic net and all these are the
Not differentiable, right?
are one of the parameters, right?
Yes, they are one of the parameters. So you can, now the loss function is combined together and you're running gradient descent on it.
And the L1 ratio, the parameter L1 ratio that you are specifying is a parameter to the penalty function.
It's a parameter to the penalty function. So first it will try to do it with L1 penalty, then it will try to do it with L2 and elastic net.
Okay.
Okay. Okay, let me just show you for some. Okay, so these are your learning rates, basically the different strategies that you have. I hope you remember constant, invariant, scaling, adaptive. This is optimal. It does not use the iteration. It does not have what we say is the power entity. It's very similar to invariant scaling if you see. Okay, it is very similar to invariant scaling. Okay, if you look at the formula. All right. So let me try these learning rates as well. I mean, if you have time, you can run it. It will take you probably 8 hours just to run everything. I'm going to use only randomized search so that I can save time. Okay. Is there anything else? So eta 0 is the initial learning rate. So here it is the initial learning rate. Okay. So this is the validation set. If you want to say that, okay, I need to use 10% data set of my train to decide whether to stop gradient descent early. So you can specify the percentage of it. Okay, default is 0.1, but you need to set something called as, there is one more argument. Yeah, early stopping. By default, this is false. So to stop gradient descent with the help of a validation set, you need to set this to true. Early stopping, it needs to be set to true. Okay, and then I'm giving the validation fraction as 0.1, which means 10% of the data from the training set will go there. Okay, 10% of the data will be untouched while training. This will be used to stop your gradient descent early. This is when you're using stochastic. So number of iterations, if there is no change, then it will stop. This is important, warm start. See, let's say you are running gradient descent from scratch. One of the problems with gradient descent is that initialization matters, right? Yes or no? Think about it. Don't you think if you initialize badly, it will take more time to converge?
Yes.
I mean, even if there is a global minima, if you initialize it too far away, it will take more time to converge, right? So imagine you ran gradient descent for 8 hours. But after running for 8 hours, you see that, okay, let's assume that you know if the function is convex. So you ran it for 8 hours, you achieved a decent solution, but it is still not close to the optimal one. Do you think if you run gradient descent again from scratch, do you think you will have a good solution? Is it guaranteed to have a good solution better than the one that you have had earlier? So let's say you ran gradient descent for 8 hours. Okay, you achieved some values of your thetas. Okay, at those thetas, you compute the error function. You compute the minimum. Okay, you compute the value of the loss function. Let's say you get 500. Now you are running, say, gradient descent for 10,000 iterations, but with a different initialization. Is it guaranteed that it would be better than what you obtained after running it for 8 hours?
No, if I don't.
It depends on where the initialization was, right? So do you feel that if I would have started my gradient descent from those thetas which I obtained after running it for 8 hours, that would be better?
Yes, yes.
So warm start is for that. Warm start means that you know what is a good initialization. So if you had run gradient descent early, you can actually provide all the coefficients as a list in this warm start. Is this part clear?
Yes.
Okay. So you can provide your previous trained model to this warm start. Okay. Average is, so this is a nice, what we say is a technique to avoid fluctuations in stochastic gradient descent. By default, it is set to false though. See, the idea in stochastic gradient descent is you are going to use one sample at a time. So can I say that if I use only one sample at a time, there might be a lot of fluctuations? I mean, if you use only one sample, the line will entirely shift to that particular sample more.
Yes.
Okay. So let's say you do it 10 times. Okay. And when you do it 10 times, the fluctuations would be very heavy. So instead of just going by them one by one, why don't you do 10 different updates and then average it out?
Yes.
That will reduce the fluctuations, right?
Yes.
So what it says is that after doing 10 weight updates, you just average those 10 weight updates across all the thetas and stop. I mean, not stop, basically, after every 10 iterations, it averages the thetas. And from that thetas, it starts again. Okay. So this is to reduce the fluctuations. Sometimes it helps, sometimes it doesn't. I'll try this. Okay. Sometimes it helps, sometimes it doesn't, because there is randomized nature of gradient descent, right? Okay. I mean, and you are choosing these samples randomly also. So I'm going to say true or false here. Okay. Once again, I need to check one thing. So I can give an integer also. Okay. So I can say false, or I can give a bool also. Okay. So any integer will, let's say if I give any integer, say 10. So it will do the averaging after 10 iterations. False means that it will not do averaging. Okay. I'm going to run I'm going to run randomized search now, just to save time. Let me use SGD in front of everything. Please note that if ElasticNet is running, alphas will not play a role. Similarly, if say L1, L2 is running, L1 ratio will not play any role. Okay. All right. Okay, let me call randomized search.
You have given L1 ratio in this params also and in this.
I'll remove that. I'll remove that. It will just be replaced. That's what this is. It will just be replaced by the parameters.
So which, okay. So
It will just be replaced by
has
this.
the more priority, the params.
Yes, those are the more priority. It will just replace it. Yeah. Okay, so import your randomized search CV. Just call this randomized search CV. It seems that you are down with flu. Is it?
Yes, badly.
Hopefully you'll recover soon. Drink warm water and probably say some medicine.
And I think it's like every week I have 2 to 3 days I have this problem.
Oh, okay. And probably then go for some homeopathic or Ayurvedic treatment. Those actually, I mean, help you recover soon. The recovery time is more, but once you get cured, you don't get it, I mean, over and over. Allopathic medicines, I mean, there is a chance of reoccurrence. So maybe this is just a suggestion to try it
Yes.
out if that helps. Okay.
Thank you.
All right. Okay. So the tolerance. Okay. So I'm still running randomized search, that too with minimalistic. I mean, I want to stop as early as possible. Okay. Let's see. Anything else that I need to specify? No, looks all good. Let me say this is randomized search CV. Okay. There is a problem here. Oh, sorry. Have I missed a comma anywhere?
It's PENALI,
Where?
the penalty, the params.
Here?
Yes.
It's called as penalty only. PENALTY. No, it says that I have. Oh, here's a dot here. That's a dot. There's one more issue. It's called param distribution. Okay, one second. Param, is it called as param distributions? Yeah. Okay. So this is training it. This is done. Okay. So these are the best params. Please note that this is run quickly. Okay. And this is the best score. Not guaranteed to have the best score. Okay. So this is because we are doing what? R2, right? So it is negative right now, which means that it's a bad model. Okay, this is the bad model. If you want to see what are the coefficients that it gets, so you can go to this best estimator. This is your stochastic gradient descent. I want to get the model which would be at place 1. Okay, this is the model, and I want to see the coefficients of it. These are the coefficients. Okay, it's a bad model right now. Okay, you need to do grid search to get the best one. Okay, it will take a significant amount of time, at least 4 to 6 hours, just to run this whole thing. Okay, this is your intercept, by the way. Anything else about this, or any questions that you guys have? Yes, any questions as such?
If it's a bad model, at what point should we start tuning? What values should we tune first?
Well, see, if you look at the artist score, it is negative, right?
Yes.
So it is, I mean, it's even worse than a constant model.
Yes.
So my recommendation is, I mean, do a grid search. So randomized search picks like at random, right? Maybe I'll run it one more time just to show you. Maybe this might get better. Okay, this is done. Okay, so it depends on what value was chosen, right? Do you see that now?
Yes, it's better.
This became better. So depends on what combination was chosen, right? So I mean, that's why I'm saying do a grid search if there are too many hyperparameters.
Okay.
Okay. And see, we are not even searching very deeply. If you think about, say, learning rate, you can go for 0.001 up to, say, I would say 0.3, and maybe take 20 values in between. I'm just doing for 5 values, right? So the better your searching becomes, the better your model will be.
Yes.
Okay, but that will take more time. So there is this trade-off. You have to decide where to stop, right? So I mean, if you run grid search on it, I mean, just wait for that time. Maybe you can do it on Colab and wait for, say, 6 hours, and once you get back, you will see the results. But please note that Colab will only support till 6 hours. I mean, drops. I mean, it restarts your kernel after 6 hours. I mean, it will. The instance will just go away after 6 hours. It will ask you to reconnect, which means that your experiments will stop. So that has a limit of 6 hours for the free version. Any other questions from anyone? So this is all about linear regression. Maybe we'll do about classification tomorrow. So our simple linear regression in detail is done. Okay, so we did polynomial, recursive feature elimination, simple feature selection using lasso and all that. You can actually take the same data set that we took last time and see if population gets dropped using lasso. We took this house price prediction data set, right? In the last class, and
Yes.
there the population was the least important feature.
Yes.
You can try doing lasso and see for a good value of lasso is population important or not.
Yes.
Okay, I mean, such experiments can help you relate these concepts with actual data sets. And these are also actual data sets, the one we are using right now, but they are not the full data sets. They are just a portion of the data sets that are used. And these data sets, they typically are giving you the important features. Once they were actually constructed, they had a lot of them. But after doing a lot of manipulations, doing a lot of search, the people who decided to keep it in your Anaconda repository of sklearn, they did it after a lot of hit and trial. Okay, so what you are seeing right now is a good bunch of features. Okay, but in real data sets, if you see, you will have to drop a lot of them. You'll have to drop a lot. Okay, so I'll stop here. If anyone has any questions, please ask. Okay, let me see if there's any here. I cannot hear either. All right, I'll stop now. So we'll meet next week. Oh, sorry, tomorrow, and we'll start with classification. There is one in the chat. Let me see. Okay, so Fazil is asking for the daily link. Just a second, Fazil. Give me a second. I encourage everyone to please ask, okay, clarify your doubts. There will come a time if you keep on procrastinating, you will not be able to understand anything. If you keep on procrastinating, see, everything is going to be related till the end. So please, yeah, I'm sharing, Faisal. With everyone, I'm sharing. Just a moment. You can bookmark it. So thank you, Shilpa. Thank you for interacting with me. Thanks, everyone. And take care of your health.
Thank you.
Bye, everyone. Yeah.
Bye.
Thank you, sir.
Bye-bye.